So we stop here and we can continue. So the next type of solar simulator is a flash solar simulator. As I told you, there are two main field of application. So first, it's to measure the concentrator solar cell, and the second to measure large modules. So here you have a simple shoulder of such type of solar simulator for concentrator solar cells. The main idea is that you have some source of the light. It's again a xenon lamp, but in this case it's a flash xenon lamp. So it looks like a similar flash. You have a photo camera, and the main idea is that you have some aperture to control the intensity, and if you move the source of light, you can change the intensity. So you can ask, what about homogeneity? The answer is that it's really bad homogeneity of the light, but as I told you, the reason is to measure to concentrator solar cells where the area of solar cells is quite small. It's a few millimeters, and actually in this case it doesn't matter. You should realize that in the real concentrator system, light is not homogeneous also, because you have a lens, you have some distribution of the light on the surface of your concentrator solar cell. So actually it doesn't matter, and there is actually a little bit another approach. So you can change the intensity mainly due to the distance. You can change the aperture, but it's something like when you create the system or produce great systems. There is another option to change the voltage of the lamp, but as I told you, it's not the range of the variation. It's quite small, because if you use too low voltage, spectrum would be different, and lifetime of the lamps decreases. The same for the higher voltage. So you have some optimal range for the voltage to make some adjustment if you need, but when you have some possibility to change the position of the source, it's actually you don't need. So actually it's like the solar simulator, like you would have some experience during our laboratory walks. The main difference of a flashed solar simulator is that you have integrated source of the light and measurement system in the one device. In some cases you can make some synchronization between the light but normally it's only one device. So if you use a continuous solar simulator, you can buy some different simulator and different devices to measure VQ. You can get a set of the different devices. But for the flash simulator, normally it's only in one, everything in one device. Device, and here is just some example to understand that actually to measure IV curve during the flash, it's quite a speed process. Everything is relative, but for example here you can see that the time is order of milliseconds, and here you have some example of timing diagram. So the red line, it's a light from the flash, so you can see that the flash actually the duration of the flash could be changed from 1 millisecond to 4 milliseconds, for example, like in our simulator. So it's quite a fast process for silicon devices, I would say, because you have to take in mind any process which is related to changing in time. If you have some capacitance of the solar cell, you should have in mind. So, but before, I'd like to describe the changes of the voltage which is applied to the solar cell. So, for example, here, first you can measure the dark IV curve, so you have some variation of the voltage, and you measure the current. So, in this case, you measure the dark IV curve. So, you apply some voltage, current. Here, it's just some way to present results. So, the photocurrent has a positive signature, and dark current has direct current has a negative. It's in opposite to the physical presentation, but that I told the first slide. So you can measure the dark IV curve, and then to measure illuminated IV curve, you have to change the voltage. So normally you start from the reverse bias, and then you change the voltage, and during this changing you measure the current. So here in this third region you measure the illuminated IV curve. And actually there is just some presentation, the simplest way to present how to manage with the source of the voltage, because you have to create some source of the changing voltage. So normally it's quite a simple circuit using resistance and capacitance, but you have to take in mind that there is some capacitance in this circuit. And if you have a capacitance, some internal capacitance of a solar cell, it means that you have influence of this capacitance to the measurements. I would stress this point because it's one of the important things for this fast measurement of solar cell characteristics. So if you want to measure 3-5 solar cells, which normally concentrated solar cell, which normally have quite small surface and quite small capacitance, actually, because if you want to look to the capacitance of the PN junction, there are two types of the capacitance. First is the capacitance of the space charge region, which is normally it's like a flat capacitor. It just the width of the space charge. Normally it's quite small capacitance. And the second one, which is most significant a direct bias, is the diffusion capacitance, and this capacitance increases with direct voltage, exponentially increase. So it's like IV curve. You have a huge increase of the capacitance with the voltage, and this capacitance depends on the thickness of your base, so the thickness of the active area, and lifetime. So there are two main parameters. So for 3-5, normally lifetime is quite small compared to silicon, and the thickness is quite small. Again, it's some few micrometers. So it's the diffusion capacitance is even negligible. I can say it's not so easy to measure it using some capacitor meter, because you have a huge current and etc. In contrary, if you work with crystalline silicon, monocrystalline silicon, high efficiency solar cells with thickness of the wafer of 200 or 300 micrometers, and lifetime more than 1 millisecond. And the area of this solar cell could be quite significant. I mean, if you measure some wafer, it's already a huge area in terms of the capacitance. The diffusion capacitance, which is normally at this direct bias, is quite significant, and this could affect the measurements. So it's some important point because every time you have to check this if the measurement is appropriate or not. It's one important thing for this flash. Seems to be similar measurement, but this transition time transition process, it's quite important. So here's a simple example. So it's a simulator, a flash simulator, quite similar. You would have some experience for concentrator solar cells. Inside you have a source of the light. You can move it to change the intensity, and you can use it to measure the characteristics of solar cells at one sound illumination, but you need calibration. And there is some example of a huge flash simulator to measure the model. So you see the difference. So it could be quite a large device, but if you want to measure a model, normally it's only a flash simulator. So it's because continuous simulator, it's crazy in terms of the power consuming. Because for example, the simulator like this, with the area of 20 by 20 centimeter, the power of the lamp is 1 kilowatt. So, and you see here the area is 20 by 20 centimeters. So if you want to measure a model 1 by 1 meter, you can imagine that it's quite power consuming light source, a few tens of kilowatts. It's crazy. So there is another type of the solar simulator which could be as continuous as well as flash, which has several sources of the light, so-called the multi-lamp solar simulator. It's something more specific. I mean, if you have the requirement to measure single junction solar cell, for example, silicon-based solar cell, you don't need some specific thing. You should not care about this sophisticated equipment. You can use just xenon lamp. It's nice, but in sometimes for more specific cases, you should have a possibility to adjust the spectrum. So the main advantage of multi-source solar simulator, it's a possibility to adjust the spectrum of the simulator. And there are different reasons. So first, the reason why do you need it? First, if you want to measure precisely the multi-junction solar cell, in this case you need pay attention to the spectrum match. And there is another reason. You can simulate the variation, the solar spectrum variation, like morning, afternoon, evening. So it's some. Actually, this is only some scientific task. I mean, in terms of standard characterization, I mean, some to get some standard reference condition, you don't need to care about it. But if you want to get in mind what would happen if I have some solar cells which is such a spectrum response, what would be advantage? So we can think about it. So there are different optical design for such a solar simulator. You can see the main problem then that if you have only one source, it's more or less a simple optical task. So you have some point source, you have some reflector, and so you can manage with more or less using traditional, some conventional approach. For multi-source, it's more complicated. So you see, it's as told, the main problem is to get homogeneous light, homogeneous distribution, special distribution of the light for multi-source. So you can use something like this. So when you have different sources, but in this case you have the problem of uniformity. So there could be some solution using dichroic mirror. So you know what does it mean, dichroic? It means that it's, for example, it's transparent for some range of the wavelength, and it's not transparent for another range. So I mean, for some range it could reflect, and for the another range it could pass the light. Another solution to use different filters near to the integrator optic. The main reason that integrated optic can mix the light, so you can try to use different filters. And for some limited area, you can use another, to my opinion, quite interesting solution. So using fiber optic. Actually, the fiber optic it's a very nice thing for many optical measurements, and you will see another solution using fiber optics. So the main idea is that you have different sources, and then it's not only one fiber. It's spot of different of several fibers. So there are a lot of them, and then you mix the small fibers, trying to provide more or less homogeneous light, and then you have this mix of sources. But I would say normally there are different solutions for multi-light, multi-lamps solar simulator, but normally they are limited in area, so you should realize that normally it's some specific thing. Here is some results, some examples. For example, this simulator where xenon lamp and two halogen lamps are used, and here you can see the different spectrum of each lamp, and here you can see the volt spectrum of the simulator. So you see it's a solid line, and the dashed line is it seems to be an opposite, because you see the monotonic is M0, and this spectrum is peaks, it's a simulator. You see, you can reach quite nice fit of the spectrum using this approach, but again, but mostly I would say it's very important for this part, because again, if you work with silicon, it's not so important, but if you work with some above silicon spectrum, it's quite important to get a nice spectrum match. Here's some example of flash simulator where I told you the homogeneity is not so important, because normally you work with quite small area and quite simple solution. You have several lamps and several optical filters. Actually, it's the same design for the simulator. You would have some experience. There are different optical filters, and there is an example. What can you obtain using this approach? So you can see the idea. So normally you have the similar source of light. I mean, have a xenon lamp, but you can a little bit adjust the spectrum to get, for example, here a 1.5D spectrum, and D it's actually because it's for a concentrated multi-junction solar cell, so normally you need D. Again, I will describe this approach. You can adjust a little bit spectrum to get the correct measurement using for multi-junction solar cells for different reference cells. It's the next topic. And finally, so the quite modern approach to use LED solar simulator. Actually, it's very nice idea, because you can find a quite wide range of the LED, and so you can create even yourself there is quite simple circuit to control, to adjust. I mean, because now it's using electronics, it's quite simple to manage with different source of light. You can use different channels, and here you can see an example that using just LED you can adjust, say, perfectly. But you see again, everything is limited by the silicon range. So if you want to even just get rough estimation of some wide range of solar cell, I mean wide spectrum of solar cell, you get nothing here. The main advantage, so as told, it's electronics allows you to control the spectrum, and actually with using xenon lamp, it's very nice in terms of the spectrum, but really not easy to control, because first of all you have to think about ignition of this source. You need a high voltage for the ignition to start the lamp, because it's discharge, gas discharge, and then you have always some kind of fluctuation of intensity. So you need some specific sources to control the lamp. And actually, if you have a look for the prices for the source, for the power source or for xenon lamp, you can see that it's quite expensive compared to any other, let's say, sources of power. And so for LED, it's quite simple, and you can adjust the spectrum. It's very nice, because you can it's, I would say, cheaper solution. You should not care about it. There is another thing which is actually also important. It's the lifetime of this LED source, because it's approximately 1 order of magnitude higher compared to the xenon lamp. It's quite important. And for xenon lamp, there is different solution, but for large simulators, normally if you change the lamp, you have to create some adjustment, some fine adjustment. You have to get uniformity again. So there are different screw. It's quite maybe not very complicated by time-consuming procedure. Here it's quite easy. And there is another thing that it's quite fast to start. I mean, for any lamp like xenon or halogen, you have to wait during 20-30 minutes until it warm up. So you have to wait. Here you should not wait, and just switch it on. And actually, producers, they told that I didn't pay attention, but normally for any simulator like this, you have a shunter. It's just because the lamp it's on. You cannot just switch off the lamp, switch on during the measurement. So you have, I told you, have it switch on before the measurements, and then to change the samples or just to avoid heating, you have to use some shunter, some mechanical shunter, which cut the light. Here, just using electronics, it's turn on the LED, and it's okay. But there is another thing. So it's uniformity, because the same, actually it's some kind of multi-source solar simulator, and the main problem is that it's not so easy to get a nice special distribution. Here is some example. It's not this, but some another simulator. But you can see the area here, for example, it's only even less than 2 square centimeters. And uniformity, you see, it's and the maximum area 25 square centimeters. So it means 5 by 5 square centimeters. So we have a limited area of a more or less homogeneous light. It's the main problem for the moment, I would say. But if you have nothing and you have not enough money, maybe it's and you have no some strict requirements, maybe it's one of the easiest way to create some simulator using LED. I would say now it seems to be a very interesting solution. So there are a lot of limitations, but and another thing concerning LED, but actually they are related, the spectrum match and this thing, that during this continuous light, for example, here it's given for 30 minutes. You see, for xenon lamp, you have some heating of the sample. So still a question, because I mean it depends on your system or the cooling system. I would say this heating is quite small, so it means that there is some cooling system for the solar cell. But for LED there is almost no heating, and actually it's quite, I would say, expectable, because once you have the limited spectrum, so you have no infrared light. I mean, infrared, of course, you have some part of the infrared, but I mean infrared, that you have no light above 1100 nanometers. So you have lower heating. It's some logical, I mean, they are related, but I mean, sometimes it's some positive point. So, few words about the methods, how to control, what should we control, and how can we do it. So, as I told you, there are three main requirements for the solar simulators. The first, it's a spectral match, and if you want to control it, you need some spectrophotometer or spectrometer. It's not so easy, especially if you work with a flash simulator. So you have to measure the spectrum during the flash, and it depends also on the range, because, for example, the spectrum in this silicon range, it's more or less achievable. I mean, using a spectrometer based on silicon CCD, it's not so expensive. It's not so sophisticated. But for wider range, it's a question, because you need indium gallium arsenide CCD. It's one of the magnitude higher price, so you see it's nice thing. And normally it's a question of manufacturer, so you can just believe to the manufacturer that the spectrum is really corresponds to that which is provided. But normally, if you want to buy some simulator, manufacturer should provide the spectrum of this simulator using the different filters. So I mean, if you buy a simulator with two filters, manufacturer should provide the both spectrum with this filter and this. So if you want to create yourself, so you have to think about a spectrophotometer or something, or just believe that, for example, the filter, optical filter, is really corresponds to that which is required. I mean, for some standard solution like xenon lamp and optical filter, so you can just believe. But in any case, it's quite. It's quite complicated thing. Temporal stability. So, of course, manufacturers should think about it, but user should also pay attention to the temporal stability. I mean, in any case, you have to control the intensity when you start the measurement, and after some reasonable time you have to control if it's really corresponds, or you have to check how does it change with time, because it's your measurement, so you are responsible. You should realize that the spectrum could be changed during lifetime of the lamp, so you should correct the intensity. The last point, the uniformity. So I will describe how to check it. Of course, manufacturer should care about some optical design, how to create the best solution for the uniform spectrum. But for user is obligatory. I mean, because if you change the lamp, if you any case, if you have a new simulator, you have to check it, and if it's necessary to correct, because normally there is some kind of adjustment of the optical design to get the best uniformity, and there is quite simple procedure how to manage. So normally you have your area, your illuminated area. have to divide it by several squares, and then using some small detector. The only one requirement for this detector is that it has linear dependence of intensity. So it doesn't matter about the spectrum much. It's so have some relative measurement, but you should be sure that it has a linear dependence. But in quite small range, actually, because you need just to perform the measurement under one sun illumination normally. And then you make a set of the measurements. At each square you made some set of this, so you measure this matrix. And then you use this known equation, as I already demonstrated, to control the non-uniformity. And if this value is not good enough, I mean, producer says that, for example, the simulator should give you 2% of non-uniformity, and if it's 5% of non-uniformity, so you can have a look how to proceed to adjust the uniformity, because normally there are some procedure, but it should be described by the manufacturer. If it's not the case, so you can call to the producer and say, okay, but your device is not really so nice as you told you. So concerning the solar simulator, for this part, it's all.